Feedback. So detecting 5G cells, this is a rambling overview. It's been a while since I've given a talk, and I have too many slides, so I'll try to be both quick and informative. So who am I? So my name is Madsen. I have a bachelor's in mechanical and a master's in electrical. So as you would expect, I write software for a living. Go figure. I started back in the day at Motorola. Initially used that mechanical degree. I did finite element analysis, thermal and reliability, got into software doing that. Got my electrical degree while I was at Motorola, and with that I transitioned to working for the GSM base station group, which does slightly date me because that's sort of an old thing. From there I worked on Motorola's first UMTS Node B, and eventually I migrated to software-defined radio. I actually used a USERP when they were relatively new, and GNU Radio course. Eventually left Motorola, co-founded Epiq Solutions in 2009, 12 years ago. It's been a good run so far. My job there, I work on cellular applications covering 2 to 5G. Done some point-to-point radio links, various signal processing things. And I primarily work in C, so I'm not a big GNU Radio person, but definitely done some waveform work, and that's what I'm going to talk about in this talk, is a waveform that some of you may not have much experience with, but is obviously very ubiquitous, and at this point will become even more so. That's 5G. Since this is a sponsor talk, I'll tell you a little bit about Epiq Solutions. We're a small company located outside of Chicago. Have about 50 people. We're growing. We have all the disciplines you'd need to do software-defined radio and software-defined radio applications. So we have people who are experts in cellular, hardware, RF hardware, software, DSP, signal processing, and we do UIs as well. So like everybody, we're hiring. I definitely want to throw that in there. Some of the products we make that you may have seen, we make a family of software-defined radios, primarily swap optimized. The form factors there, mini PCIe and M.2, so these are very small, high-performance radios. We have some more capable systems based on VPX, FMC platforms, with more channels, more bandwidth, all the bells and whistles. Our software side you may know less about. We have some applications focused on security. Flying Fox is a wireless detection system, and Skylight, which actually is where the genesis of this talk came from, is a cellular survey application. So why would you want to detect 5G cells? So detecting a cell is the first step for many applications. There's obviously commercial cellular survey, like I mentioned, that we do. It's used for drive test, installing equipment, configuration and provisioning. The government applications, primarily related to kind of knowing what's out there when you roll into a new area, public safety related things. And of course, there are people who want to do bad things to cellular networks and communications in general. So detecting threats to networks is an important aspect. And more in this area, for you guys, I know education and research is a big deal. And in my opinion, cellular does represent the state of the art for wireless communications. A lot of very smart people work on it. A lot of money goes into it. There's literally billions of devices. So if you can understand how cellular works, you'll probably learn something useful to apply to your other wireless applications. So this talk, very fundamental thing, how do you detect something? So there's 3 basic steps. You're going to capture some IQ at the right frequency and sample rate. You're going to correlate it with something that should be present in the signal that you're looking for. And if you got a nice peak, you found something. So not super complicated. In more detail for 5G specifically, what I'm going to talk about is there's a lot of acronyms and numerology in the cellular world. So I'm going to cover some of that so you have some insight into how that works if you've never seen it before. There is a specific sequence for 5G called the SSP PSS that you need to generate. And if you do a correlation with that and you have everything else right, you'll get a nice peak in your correlation. And that means you've found a 5G cell. So we'll start with the boring list of acronyms here. So somebody out there, I'm sure, made a lot of money coming up with the acronym NR. It stands for New Radio. Yes, so much better than 4G, which was long-term evolution. But somebody in this room may come up with the acronym for 6G, so keep that in the back of your mind. You could be that person. So there's something called FR in NR1, stands for frequency range. There's 2 frequency ranges for 5G. FR1 is the lower band of roughly 400 megahertz to 7 gigahertz. That's sort of associated with traditional cellular. They added something new up higher, FR2, also known as millimeter wave, from 24 gig to 52 gig. So definitely up there. Bands and channels are a big thing for cellular systems. For NR, the bands can be either TDD or FDD. They have downlink bands and uplink bands. For FR1, sort of the way they number them is they start with an N. So there's N1 to N99. And there's some gaps in there. There's not 99 bands, but it is a lot. FR1 is those, and the channel bandwidths associated with those bands are anywhere from 5 megahertz up to 100 megahertz. So there's a lot of flexibility. FR2, the millimeter wave, has higher band numbers, and the channel bandwidth, because it's up higher, is much higher. So the minimum bandwidth for those bands is 50 megahertz up to 400 megahertz for a channel. And one convenient thing to know is if the band number is the same as the LTE band, it's the same frequency range. So if you already know some, you know some NR already. There's 3 primary acronyms you want to know when talking about NR channels. The least useful is NREF, but it's the most fundamental. NREF identifies frequencies on a raster. Below 3 gigahertz, the raster is at 5 kilohertz, and above 3 gigahertz, 15. The next one's probably the most useful and common is NR ARPSN, absolute radio frequency channel number. That's basically a set of valid NREFs for a specified band. It's not simple. It's literally pages in the spec because they have exceptions and qualifiers, but that's the term. The final one I'll come back to later, but I'll mention it here. It's GSCN, the Global Synchronization Channel Number. It's a subset of NRFSNs and some other frequencies, NREFs, that are valid for specific type of network called a standalone network. So where do I get all this information? So the internet has everything, as you would expect. And in particular, the website 3gpp.org is where you want to go to get specifications for 5G and all the earlier ones. So 5G is defined by the 38 series, radio technology beyond LTE. There's a lot of detail in there. I put a little snippet of a spec defining the GSCN, which is, by the time they get to that, they're already on page 49 of a 400-page document that's just about how channels are numbered. So, like I said, there's a lot. There's also some calculator sites out there that are pretty useful. And there's other sites that have done a really good job of going over 5G. And I mentioned some of them in particular because when I was putting these slides together and wanted some pictures, people have already done some great pictures, so I kind of borrowed their images. All right, speaking of images, I love 5G memes. We live in a time where we're lucky enough to have memes, and people have decided 5G is worthy. So this is the 5G horse meme, if you haven't seen it. If you happen to see a horse made of pure energy wandering around, that's actually 5G. Now you know. Okay, some more boring numerology. For those of you that worked with OFDM before, this should look familiar. You know, you got your resource grid on the x-axis. I'm talking about the picture in the middle of the slide there. You got the symbols on the x-axis, and on the y-axis you have your subcarriers. So very typical OFDM, nothing complicated there. For NR, they've divided things up where there's 100 frames a second. Each frame has 10 subframes, and then there's some number of slots per subframe. That's the picture in the lower left. So depending on the subcarrier spacing, the subframe duration, the slot duration changes. So you have from 1 to 16 slots depending on the subcarrier spacing. And again, this is just to give you some overview of what you're looking at. Basically, if you've seen OFDM before, there's just details. So these are some of the details. Okay, so now we cover bands, channels. You can look up a frequency, figure that stuff out. There's one more thing to cover before I talk about what we're actually trying to detect. And that is that there are 2 types of 5G networks out there. There are standalone networks and non-standalone networks. So non-standalone means that the 5G network is actually still using LTE for the packet core, sort of the part that transports the data and where you register and all that fun stuff, networking. So they did that, of course, so that people, the people installing all this stuff wouldn't have to redo everything all at once. They used the LTE core with 5G user plane. Standalone network, obviously, it's just everything's 5G all day long. So one of the interesting things about this is that a non-standalone cell can be on any valid NR arfsen, and some of the bands are very large, in particular the FR2 and some of the TDD bands in FR1. So I think because of that, and because they're using the LTE for the control signaling, the LTE anchor actually tells the UE directly where to go for 5G by sending in a message saying, go to this NR arfsen. The UE does not have to find it. And for standalone, I should say also there's an interesting little detail here that a non-standalone network, NR network, can be overlaid directly on top of LTE with something called dynamic spectrum sharing. So they literally share the same spectrum and coexist. LTE, of course, is not aware that NR is there, so it has to be sort of faked out to create holes, and then NR lives within those holes, which is interesting that they got that to work. So the standalone, I mentioned before the GSCN, on the standalone network, there is no LTE anchor to tell you where to go. So that's why they use that GSCN raster, because it's much coarser, a lot less channels to check. All right, speed this up. What are we trying to detect? The synchronization signal block. So that's transmitted for both types of network. It's always present. It's OFDM. You got to figure out what the subcarrier spacing is. They didn't keep it simple. So FR1, it's going to be either 15 or 30K. FR2, it's going to be either 120 or 240. And if it's non-standalone DSS, which is mostly what's in use right now in the United States, it's going to be 15 kilohertz, because that's what LTE is. Here, finally, we've reached the picture of the SSB. The SSB, and this is that same kind of like OFDM style diagram. So you got symbols on the x-axis, subcarriers on the y. So you got 4 symbols worth of data. The first symbol contains the PSS, which is the primary synchronization signal. Then you've got the start of your PBCH, which is the broadcast channel that contains the MIB, which is the master information block. Finally, you got a secondary sync. It's interesting to note, different than LTE and every other preceding standard, this signal does not have to be in the center of the channel. It can be located at an arbitrary NR arfsen or GSCN. So that introduces some confusion. It confuses me. Definitely makes things a little more tricky. They use weird terms like offset to point A. You're like, what's point A? I have no idea. But that's not important right now. The PSS itself, finally, very simply, only is one of 3 possible sequences, which is transmitted, like I said, at least every 20 milliseconds. It's real valued. It's specified in the frequency domain. I've generated and given you the actual sequences and also put a picture of the math. It's not super hard to generate. So now we have everything we need. So some more memes to fill up the rest of my time that I don't have. So we got 5 guys, which is what actually killed Uncle Ben, right? It was the 5G. Okay, so you're out there with your laptop. You got your radio. You're going to capture some data. You need to know what band. So you got to look on the internet. You're going to find out the US uses a certain subset of bands. You're going to go to Wikipedia. You're going to look up their network. There's a list of what network is on what band in Wikipedia. You're going to go to the coverage maps for the carrier. You're going to see, hey, do I have it here or not? This is what we had to go through at Epiq, when we first tried to find 5G. I drove downtown when they turned it on. I'm in my car with my computer looking totally, innocuous. Nothing weird's happening. It's a good way to have police like a slow roll by, it turns out. So you want to capture at the right sample rate. That's the one thing I haven't covered yet. So like I said, it's probably going to be NSA on top of LTE. So it's going to be 15 kilohertz. We want to capture the entire SSB. So 256 point FFT, multiply it out, 3.84 megasamples. Good to go. Here's the spectrum view of band N5. I think I got this at my house. So you can see there's a number of, exactly what you'd expect. There's a number of channels going on. Who knows what they are? Well, I'm lucky. I have access to a survey tool that does LTE, so I can cheat. And I can tell you that widest cell in that picture is a 10 megahertz LTE cell at a particular frequency. So I can figure out in that 10 megahertz bandwidth, there's a certain number of possible places that SSB can be, and I can either capture on those individually at that right sample rate, or I can do a wideband capture and channelize, whatever your favorite method is. You just basically got to get the data in and then look at it. So here, I've pulled in some data at a specific NR arfsen in that LTE channel, and I plotted it slightly differently. You can see, there's some stuff that looks like data there. There's some repeating stuff that crosses the entire bandwidth that could be an SSB. And sure enough, on the bottom graph, it's like impossible to see, but there's some really beautiful correlation peaks every 20 milliseconds. So we did it, and on the far right there is a frequency corrected and time synchronized view of the SSB that was detected. Looks just like textbook perfect, so it all works. All right, how much time I got left? Definitely have too many slides. So we've detected 5G. We now have a 5G cell that we know we can find. If you wanted to keep going, there's a lot more steps you can do. The next step, of course, is to look at the secondary, same type of math. Instead of 3 possible values, there's 336. So you figure out which one it is. There's a little formula there in the bottom right. From that, you can get the cell ID, physical cell ID. Then you can try to recover that PBCH. So I stole a nice little diagram here from MATLAB, and shout out to MATLAB. They have a nice NR toolbox, but they also have a lot of great stuff on their website just about how NR works. So you're going to try to recover that PBCH. You're going to do traditional OFDM type stuff, right? You're going to frequency correct. You're going to want to equalize based on some kind of reference symbol. So NR uses reference symbols that vary depending on something called the ISSB or beam index. So this is a good time to talk about beams. I know Matt Edis gave a talk earlier about beam forming. NR is all in on beam forming. It's a little confusing, but the basic idea, like I said earlier, you know that there's going to be an SSB at least once every 20 milliseconds. It turns out there's 8 different ways you can send SSBs depending on the frequency, the band, time of day, I don't know, all kinds of stuff. And they have these different ways, and the idea is that each beam index is actually sent in a different physical direction. And that's what the picture on the right is trying to show, that a UE will receive different beams at different signal levels and can figure things out about how it should get additional data once it's decoded the control channels. So that beam index is used to locate and determine the values of those reference symbols. The picture on the far left there shows how they move around. It gets a little involved. The people who write these specs love these kind of intricate little formulas where everything depends on everything else. I don't know, it's I think they get patents or something. It's almost like there's a reason. So what do we need to generate these reference symbols to try and figure out which one it is? We need the cell ID, that's one of the factors. We need the maximum number of beams that there could be, which you get out of the spec. That depends on the band, the frequency, the subcarrier spacing. For each beam, you have to try all of the possible beams, which is up to 64 for FR2. And then they add yet another little wrinkle. They say, which half frame are you in? So I still don't quite understand the half frame thing. Even though it sounds so simple, you'd be surprised. So you try all of the possible options here. One of them is the winner. And you can equalize the entire SSB. So here I'm showing finally some recovered symbols. So the first symbol is that PSS. Once it's cleaned up, it's BPSK with nothing on either side. The second symbol on the bottom there is the start of that PBCH, where it's sent as QPSK. The third symbol, we see the secondary in the middle, surrounded by a little bit of PBCH, so that's a little harder to see than I would like, but it's a big kind of a hybrid constellation of QPSK plus BPSK. And finally, you wrap up with the rest of the PBCH. Okay, so we haven't even gotten started, because it turns out to recover that PBCH and get to the MIB, the master information block, you have to go through all these other steps that are pretty common in digital telecommunications. So we just did the demod to get our symbols. So you have soft decision at that point. You're going to do descrambling. You're going to rate match. You're going to do a polar decode to get bits. You're going to do a 32 or 24-bit CRC, descramble, de-interleave, And after all that, you've gone from 432 QPSK symbols down to 32 bits. So there's just a small amount of redundancy in this transmission, it turns out. And even of the 32, it turns out only 24 are the actual payload. And there's a bit in there called the half frame bit. When I mentioned the half frame bit was confusing, it's because it's like it shows up twice. They never agree. That 24 bits is actually only 23, because one of them is an extension field, so they can change it later. And that is encoded as ASN1. And there it is. And once you get there, it actually, you probably can't read it, but I'll just cut to the chase. It's a little disappointing because none of this is information you actually want, all right? You're like, where's the mobile network code? Where's the country code? It's nowhere to be seen. It's these slightly obscure parameters like DMRS type A position. You remember I mentioned offset to point A. Cell barred, okay, is the cell on or not? A spare bit, well, that's useful. So there's just not a lot. What this actually does is it points you to SIB1, which is where all the good stuff is. And I took another picture here from MATLAB, MATLAB's website. This is how you recover SIB1, and it's about like 10 times more complicated than what we just went through. So let's get going here. I do have no, I'm not gonna actually go through it. What I will say about SIB1, like I said, it's interesting compared to previous generations that SIB1 is the only one that's guaranteed to be transmitted as an actual broadcast message. The other ones don't have to be. They can be broadcast on demand when requested, but still broadcast, or they can go over dedicated signaling. So it is like a fundamental shift in kind of how that control configuration information flows from the network to the UE. This talks about how do you get to that SIB1, and like it can be located in 1,000 places, and there's just so many options, which is what makes it so complicated. And the actual message, it's up to 2,796 bits, so a little bit more. And you finally do there get, the information like, hey, who's the carrier? What network is this? How do I page the network? What kind of channels do I have access to? What are the control channels for everything that needs control? And that brings us to final thoughts. Hopefully I'm not going right now. It's been a while since I got my shot. And I would like to mention, we are hiring. If this kind of stuff is interesting to you, if you like, cool hardware that's really small and capable, if you like working on challenging problems with people who are excited to solve them, things that actually go out the door and make a difference in the world, come talk to us. We have a booth. It's all good stuff. And thank you, GRCon21.